Dear all, welcome to the presentation of the paper Shotcrete 3D Printing Technology for the Fabrication of Slender Fully Reinforced Freeform Concrete Elements with High Surface Quality, which I'm presenting today on behalf of my co-author Harald Kloft and myself, Norman Hack, both from the Institute of Structural Design at Technische Universität Braunschweig. In 2016, the Institute of Structural Design has put the Digital Building Fabrication Laboratory into operation. This unique laboratory enables investigations on the large scale of construction and facilitates both subtractive as well as additive fabrication processes. These operations can be performed either independently or simultaneously and collaboratively. Shortly after inauguration of the lab, we started investigation an updated version of the well-known and well-established shotcreting technique. The advantages of this technique are, firstly, that the concrete sticks well to vertical surfaces, secondly, that it can be sprayed around reinforcement, and thirdly, that the high velocity of the projection compacts the material very well. On the downside, however, is that the shotcreting process is generally very dirty, often comes with high material loss, is rather imprecise, and additionally is quite labor-intensive. In the following slides, I will elaborate how this can be changed using robotic automation processes covering the entire workflow from initial application to surface finishing. With robotic control and advanced sensory capacities, the aforementioned disadvantages can easily be eliminated. What you can see here is how a line laser measures the distance between the printed layer and the nozzle. If the layer detects a deviation from the target distance, the robot's speed and hence the application volume is automatically adjusted. Using such feedback routines, the shotcrete process can be well controlled and precisely executed. As can be seen in this video, the disturbance, in this case deliberately caused, can be compensated after only a few layers. With our current setup, we are able to print approximately 1 cubic meter of concrete per hour. This relatively high building rate is possible due to the fact that a concrete accelerator is added at the nozzle, causing the concrete to build up strength directly after its deposition. Another unique feature is the ability to print cantilevers onto vertical surfaces. In this example, the console is printed perpendicular onto a vertical wall. This, of course, is not ideal for the continuous transmission of forces, which leads to another aspect of Shotcrete 3D printing, namely the possibility to print gradual transitions from the vertical to the horizontal plane. In that way, throughout the structure, the full cross-section can be used to transmit forces, similar to the concept of compression-only arches depicted in the diagram below. As most structures are not in compression only, the integration of reinforcement is a critical issue in 3D printing. For single curved structures, we have successfully tested the use of carbon fiber mats that are pressed onto the printed core structure and are subsequently covered with a second layer of concrete. Ultimately, surface finishing is an issue that needs to be addressed, particularly as Shotcrete 3D printing delivers rather rough surfaces. For this, we've tested different surface troweling strategies, as for example the rotating steel disc shown in the video here. The multitude of techniques which we have developed over the past 3 years have recently been integrated into the design of a final demonstrator. Furthermore, the novelty of that demonstrator is, a reinforcement strategy that allows the integration of structural reinforcement in both principal directions, also for double curved concrete elements. The strategy here is the following. First, an undulated version of the intended geometry is printed, whereas every 40 cm a pre-bent horizontal reinforcement element is manually placed. Over the entire height of the structure, this creates vertically aligned channels with loops formed by the reinforcement. In those channels, the vertical reinforcement can be inserted. Subsequently, an additional layer of concrete is added, which does not only act as a final surface layer, but which also structurally embeds the reinforcement. And finally, the surface is smoothed using a set of different rotating discs of different sizes. Okay, so much for the theory. In the following, I will show you selected images of this process. Firstly, we have the core printing in its undulated form, and on the right, the pre-bent horizontal rebars. In this case, we welded some steel pins onto the rebar in order to keep the rebar in the right position. Then, after printing the core, the edges are cut to precision using a 12 mm flank milling bit. This process is later repeated after the second layer is applied. Then the vertical reinforcement is simply inserted. This is a process that consumed less than 5 minutes of time, as the vertical reinforcement doesn't require any additional pre-bending. In a fourth process step, the second layer is printed on top of the core, structurally embedding the reinforcement. And finally, the surface is smoothed using rotating steel discs of different sizes. This is done until the surface reaches an acceptable quality. In this case, it required 5 iterations. So, without further ado, I will now present you a short movie about the entire process, say thank you for your attention, and hope you enjoy the rest of the conference. Thank you and bye-bye.